Example 5 from section 8.3 illustrates an integrand that does indeed contain a secant and a tangent factor. But in this case, the power of the secant is even, and that's going to cause us to obey one of the guidelines that's illustrated in the gray box that accompanies the notes. And the most important thing about that particular guideline is when you have the even power of secant, that you want to save a secant squared term. Now, the way that we're going to do that here, as we've done with many problems before, is to rewrite this integrand, the secant to the fourth especially, into two different parts, a secant squared times a secant squared. And I'll tell you what I'm going to do. I'm going to go ahead and let this tangent cube sort of position itself between the two secant squared so that I really have them nice and separated. Now, at this point, the secant squared here at the end we want to keep intact because our goal ultimately is to eventually let a u perhaps be a tangent factor whose derivative would result in a secant squared. Now, in order to let u be a tangent, then without question, we would want the rest of this integrand to contain nothing but tangents. And we will be able to accomplish that by rewriting the secant squared of 3x using the Pythagorean identity. And since we know that secant squared is 1 plus tangent squared, that'll be a pretty easy thing to pull off here. The only thing that you want to be careful of is that we're not dealing with just the variable x, but 3x. So secant squared of 3x would be 1 plus tangent squared of 3x. Everything else just follows. And then, as in typical fashion, we will go ahead and use a distributive property here to bring our tangent cubed back into our binomial. So we would have tangent cubed of 3x plus tangent fifth of 3x, tangent to the fifth of 3x. And still this secant squared of 3x sits outside, waiting to be utilized. And that time has come now because we'll let the u become tangent of 3x. Like I said, the motivation behind this is the fact that you'll have no trouble integrating a u to the third and a u to the fifth. They're two very simple power rules. And the choice of our u being tangent of 3x helps quite a bit in establishing the relationship with this secant squared of 3x. Finishing out our derivative of the u, the derivative of the tangent of something is secant squared of that something, 3x, but we must multiply by the derivative of 3x to complete our chain rule. So we have a very nice match here with our du, other than the fact that there's this 3 out in front that we can easily fix by bringing it to the beginning of our integrand as its reciprocal, 1/3. And if we integrate now everything with respect to u, our rewrite, as I said before, will leave us with u to the third plus u to the fifth, all with respect to u. Very easy integral to take, as it gives us a u to the fourth over 4 plus a u to the sixth over 6. And as always, we're obligated to go ahead and do our back substitution here. And I'm going to let tangent of 3x now plug in for the u's here. And there's something else I'm going to do with this to get you a little bit used to the kinds of simplifications that you could see with the back of the book, the solution manual, and a lot of multiple choice answers. And it's a little kind of a pesky type of simplification. It's something that you can all handle. It's basically an Algebra 1 based type of factoring along with the trigonometric factoring. The question is, do you want to do the factoring now with the integral's answer in terms of u, or do we want to do it with the integral in terms of tangent of 3x? Well, it really doesn't make any difference. If you feel more comfortable dealing with the algebra and not the trigonometry, it might be best to go ahead and perform the simplification at this point. And really what it's all about is just getting a common denominator. You know, if you see a 4 and a 6, immediately you should know that the common denominator that you would most likely use would be a 12. So what I'm going to do is just kind of rewrite this 4 as a 12 and put a 3 in the numerator, and do the same here with this 6 by putting a 2 in the numerator. Now what that's going to then sort of clue me in on is the fact that I can factor out a 1/12 that will join my 1/3 already out in front to give me a coefficient of 1/36. But I'm not done yet, because you can see that within this brackets we have a pair of u's, one of which is raised to the 4th, one of which is raised to the 6th, so we can factor out the common factor there. In this case that would be the smaller power, u to the 4th. And then upon doing that I would have a 3 and only a 3 left over from my first term here, and then in my second term the 2 would stay along with a couple of powers of the u. Now once that factoring has taken place, it's quite simple to go ahead and back substitute my tangent of 3x. So I would have the tangent to the 4th power of 3x along with my 1/36 times 3 plus 2 tangent squared of my 3x. And of course we would have to add our constant of integration, plus c, which I'm not so sure if that plus c showed up, so I'm going to make sure I put it down there since it's kind of getting off to the right edge of my screen. Now, like I said, there's absolutely nothing wrong with an answer that doesn't have this strange sort of factoring to it. But just to prepare yourselves to be, you know, very adept at taking the multiple choice format type of quizzes, you're going to want to become very comfortable with that. You would never ever, however, be asked to perform a simplification like that if the problem was in a free response setting, though.